Before we jump into the engineering perspective, I want to provoke some thought by asking, what makes a good meal? To do this, I'm going to compare the McDonald's Big Mac to the In-N-Out Double Double. Both of them are burgers, and they have relatively the same ingredients, but they're going to have different texture, taste, and a level of quality. This is because McDonald's prepares their burgers differently from how In-N-Out prepares their burgers. So what we see here is, it's not the idea or the components that makes the burger, but rather how we use those ideas and components to make the burger. It's the process that matters. And similarly, as engineers, our effectiveness and quality is going to come from how we prepare our products. That's what the engineering design process is for. As an engineer, you're going to want to know these steps in order and know what happens in each of these steps. It's a lot easier to break them down into subgroups. Based off of rows, for example, I like to see this as planning, testing, and finalizing. Once you have them down into subgroups, you can then remember what happens in each of the subgroups and then what happens in each of the steps. However, I find in practicality that planning is the most important subgroup. The more time you spend in planning, the less time you'll have to spend in both testing and finalizing, which means there's less resources and time that's spent in the long run. In the planning subgroup, we're trying to give our product some shape. To do this, we have to consider as many details as possible. In this example, I want to create a gigantic fighting robot. Well, I've already defined my purpose, however, defining it further will allow me to make my robot more effective. For example, if I said that I wanted to make a gigantic fighting robot that fights as a one-piece brute force style, I would pick the robot on the left. However, if I wanted to pick a more agile and precise robot, I would pick the robot on the right. These both accommodate two different fighting styles and are going to be more effective to those who have very similar fighting styles. It comes down to fine-tuning your purpose. Once we've well defined our problem, we now need to figure out how to solve it. Knowing what specifications our products must have, what factors affect our product, and looking into similar previous failures and successes will help us solve our problem. The last of the three is known as literature review. These images demonstrate what I just talked about. The first image on the left demonstrating how the designer took wear through movement into consideration by choosing cardboard as his material of choice. The middle image is a step above and not only notices this factor, but also thought about the specifications of the original robot. He resized the dimensions to his height. Lastly, the image on the right also went a step above and used literature review to figure out what techniques and tools failed and succeeded on getting the colors, textures, and lighting that they have in the image. After we spend a good amount of time planning, we now want to create a model or models to make sure that our idea works. The more details that we put into our models, the more problems or flaws that we'll be able to catch. In the case of our models of the tank, we can see the relational size of the soldiers and even all the components that make up the tank. This means that we'll be able to diagnose our problems to each component if we have any. Once we have a greater understanding of our model, we then want to simulate it, keeping in mind that both modeling and simulations are supposed to minimize the amount of resources and time that we spend on the actual product, which is extremely important when we're talking about computer chips or airplanes that cost millions of dollars to produce. Remember though that the consumer is not paying for the cost to produce the product, but rather for the assurance made through the engineering design process. After we're sure that we have most if not all the problems worked out, we will then build a 1-to-1 scale prototype to make sure that all factors have been addressed at this scale. This is still less expensive than producing the final product, but is more expensive than creating both models and running simulations. Only after we're sure that our product will deliver, we now need to dumb down our product, or in other words, make it user-friendly, by making some sort of simplified user interface. The simpler the better. In the case of the Blendtec blender, we have to assume that the user doesn't know what increasing or decreasing the RPM of the motor will do, and instead, we have to add buttons that give functionality to our product. There has to be a blend button. After we've added these components that make the product user-friendly, we then want to do final tests to make sure that all the functions happen as expected, which is known as black box testing. This is because you can't see inside of the product, but know that it should output what the specs state. Again, we're being paid not for our ideas, but making sure that our ideas actually work. So again, my advice to you is get to know the steps in order and know what goes on in each of the steps in the engineering design process. Now we're going to cover binary, which is just a representation of on or off, which is represented by 1 when it's on and 0 when it's off, just like a switch over here. This graph just represents when voltage is high and when voltage is low, of course high being 1 and low being 0. Hopefully at least once in your life you've come across a door with locks on it, or at least an electronic door. That's exactly what an AND gate or an OR gate is. An AND gate is just 2 keyholes on one door. You have to have 2 of the right keys to open up that door, and if either one is wrong, you're not going to be able to open up. An OR gate, on the other hand, I can have as many signals as I want, and as long as they are the correct type of key, for example, the door in front of BYNG, a student ID is all that you need to open up that door. Of course, we have millions of students, but you need to have SID-C access. As long as that SID-C exists in the signal, you can open up the door. Knowing what an AND gate and an OR gate looks like is extremely important, especially in future classes, but the symbols on the other hand are going to be different in every application, and those will be explained more in depth when you actually get to the Boolean algebra and also the code behind it. All the gates that we've covered so far are referred to as primitives and can create all combinational logic. Next on that list is the NOT gate. This is a buffer connected to an inverter, the circle being the inverter and the triangle being the buffer. A buffer just refreshes the signal, and this is because it's directly connected to the power supply, which means that if I have a long path of logic gates, I can assure that my signal will be a clean high or a clean low by using a buffer. This isn't important right now, but in the future you're going to have to know this. An inverter, on the other hand, just does exactly what it sounds like. It changes 0 to a 1 and a 1 to a 0. So just know that a NOT gate for now changes a 1 to a 0 and a 0 to a 1. Now, with that in mind, we can create the NAND gate and the NOR gate by just adding an inverter to an AND gate or an OR gate. And this means that a NAND gate is just an AND gate with inverted outputs, and a NOR gate is just an OR gate with inverted outputs. However, it's extremely important that you don't memorize the truth table and that you understand what is going on in each gate. Remember that every time you see a gate, to see it as the gate and to see a circle as an inverter. And to demonstrate this, we're going to take our OR gate and AND gate and invert the inputs. Even though you would expect the OR gate to be a NOR gate by inverting the inputs, it actually does the opposite. By inverting the inputs, I'm actually changing it into a NAND gate. And if you go through the logic, let's say for example that I took 1 1 as my signal, then I'm going to now put 1 1 through the inverters, and that means that my 1 1 becomes a 0 0, and a 0 0 into an OR gate is just a 0. Now this matches up exactly with the NAND gate's truth table, and this means that when I use inverted inputs on an OR gate, I get a NAND gate. Similarly, I can make a NOR gate by inverting the inputs of an AND gate. All the primitives before this have used one logic gate or logic gate connected to a NOT gate. Now we're going to use a combination of these gates to create one primitive. And this is why this is referred to as combinational logic, because I'm attaching a combination of logic to create more logic. This primitive is known as the XOR, and knowing the insides of it is a lot more complicated than knowing what it actually does. Again, you can go through these gates on your own to understand what the primitive is actually doing. Like we discussed in the engineering design process, engineers are lazy, and it would take way too long to draw this XOR by all these gates. Instead, we have an OR gate and an extra curve added to our OR gate. And this is going to be referred to as the XOR or exclusive OR. And what this means is the only time you're going to output a 1 is when you have one and only one of the signals giving a 1. Another way of looking at this is a coin slot. If you have two people inserting the same coin at once, they're going to jam the slot. But if you have one person inserting a coin and then the person after that inserting a coin, then each coin will go through. And finally, we have the XNOR, which is just the XOR or exclusive OR added again with an inverter at the end. So it's the reverse of the coin slot, where only when two people insert it at once or when nobody inserts it at all. Or in other words, when there's no coins inside of the machine, it's going to output a 1. Now that we understand the primitives, let's use the XOR. The XOR is actually exactly how we add in binary. And to demonstrate this, I'm going to first add in base 10, which is decimal, or which is what you've been using in every standard math class. Now 9 is the highest digit in base 10, or in other words, I go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's no 10 after 9. That means I have to start over from 0. And what this means is if I increment 9, that means I have to start over from 0. But I'm actually incrementing the next bit, or in other words, I'm incrementing the tens place. Similarly, I have to do the exact same thing to base 2. When I go past 1, nothing is past 1, it just goes 0, 1, and then back to 0. But I have to increment the next place, or the 2's place, or 2 to the first place, however you want to look at it. But when we add in base 10, I'm not just incrementing, I'm carrying. So I'm going to add 9 plus 1, I get a 0 in the 1's place, and carry that into the 1 in the 10's place. Similarly, I'm going to increment my 1 and turn it into a 0, and carry that 1 into the 2's place. So I get 1, 0. Again, 1, 0 in base 2 is different from 1, 0 in base 10. I'm really saying 1 times 2 to the first plus 0 times 2 to the 0th is equal to 1, 0 in base 2. And similarly, I'm saying that 1 times 10 to the first plus 0 times 10 to the 0th is equal to 10 in base 10. Because A and B are both 1 bit, our sum should be also in 1 bit, and our carry is another bit. The carry is referred to as the most significant bit, and the sum is referred to as the least significant bit if you were to append both the carry and the sum together. And the order would be from left to right, the carry, and then the sum. However, remember that really our sum, again, should only be 1 bit. And this is because if we were to add 3 plus 5, we're going to end up with 8s only in the 1 spot. And so that means if we don't add the carry as an output, we won't have that extra bit, our most significant bit, and should only have the sum. Of those topics, that's everything that's covered in the lectures, so feel free to stop here if you want, but I find that converting decimal to binary and binary to decimal is extremely important. You'll learn it in future courses, but if you learn it now, it'll be a lot easier then. Again, remember that each binary bit represents a switch, so this means that each switch has 2 combinations, and that means that if I have 4 switches, for example, I'll have 2 times 2 times 2 times 2 because each one has 2 different combinations. So in other words, I have 2 to the 4th total combinations. So in order to convert from binary to decimal, what I'm going to do is, like I just mentioned, convert this into 2 to the something power. So we'll convert 1001 in binary to decimal. And to do this, all you have to do is take each bit's exponential, of course, all the way to the right being 2 to the 0th, and then take each one and multiply them by 0 or 1. For example, in this case, we'll have 1 times 2 to the 3rd plus 0 times 2 to the 2nd plus 0 times 2 to the 1st plus 1 times 2 to the 0th, which ends up being 8 plus 1 in the end after you simplify things out. Converting from decimal to binary is just as easy. All I have to do is divide by 2 in each step and then take the remainder, and the remainder will be one of my bits. Now to convert 9 base 10 to binary, I'm just going to again divide and then take the remainder as my bits. So first step, 9 divided by 2 is equal to 4 with 1 as my remainder. I'm going to take that 4 as my next division. 4 divided by 2 is equal to 2, remainder 0. Do that again, take that 2, move it over there, and then divide by 2 again. 2 divided by 2 is equal to 1 with 0 as a remainder. Take that 1 and then divide by 2, and then end up with 0 as my result and a remainder of 1, and that'll be my most significant bit. Again, most significant bit means all the way to the left, and least significant means all the way to the right. I hope this helped you out, and if you have any confusion, questions, comments, feedback, or want any other topics covered, please leave them in the comments below, and most likely I'll be making your final review in the same format as this video, so stay tuned for that.